Welcome, everyone. My name is Maciej Stowski. I'm the head of scientific services here at Pawsey. And today I have a great pleasure to facilitate Meet the Quantum Pioneers seminar. But before we start, in the spirit of reconciliation, we would like to acknowledge the traditional custodians of country throughout Australia and their connections to land, sea, and community. We pay our respect to their elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islander peoples today. Welcome to the event. Today's event is the third of a series, which started with Why Quantum back in May 2020, followed by Quantum Computing for Industry Growth in August 2020. If you are new in the quantum computing world, we encourage you to watch the recordings of these events on our YouTube channel. Research and technology is one of the Pawsey strategy pillars for 2020-2025. Its focus is on preparing and applying current and future technologies that deliver peak performance for research insights and understanding. Our quantum engagement in translating into development opportunities for staff while exploring its impact among the research community and its potential when working alongside existing and future HPC systems. Today's event is an opportunity to share an update on Australia's first quantum supercomputing hub for innovation and the collaboration established between Pawsey and Quantum Brilliance in May 2020. Today's discussion includes the relevance of quantum technologies at Pawsey, Pawsey's collaboration around these technologies, and then we'll be giving some details about our collaboration with quantum computing hardware startup and information about the scientific and industry projects supported through the Quantum Pioneers program during the evaluation and full-time phase. You will hear from the groups invited to the program. They have been granted exclusive access to Quantum Brilliance emulator available on Pawsey's Nimbus Research Cloud. Moreover, they will also have exclusive access to the world's first deployment of a room temperature diamond quantum computer hosted in the HPC Center for Open Science and Industry here at Pawsey. Let's hear about the science behind it and its applications. First, I have a great pleasure to introduce Ugo Varetto, Pawsey Chief Technology Officer. Ugo Varetto is an accomplished manager bringing international experience, including computational science, research, supporting complex distributed software solutions, software engineering and development, architecture and testing to Pawsey. His focus is particularly on data-intensive high-performance computing, interactive distributed visualization solutions with real-world experience of leading distributed teams across several continents. He has held key roles in significant projects such as EU-funded Human Brain Project, and also contributed to numerous research projects within European supercomputing infrastructure. Ugo will talk today about our quantum computing journey and its importance. Over to you, Ugo.
Yeah. Thank you, Maciej. Yes. So this is going to be a short presentation just to introduce the Quantum Pioneers program, explain why we started looking at quantum computing technology, what we have been doing and plan to do in the future. First question is, of course, why quantum? Reasons for looking into quantum computing technology include growing interest. We have experienced an increasing demand for supercomputing allocations from researchers working on new quantum algorithms and simulators. Growing availability. Today, you can access quantum environments on all the major cloud platforms. Then, of course, there is this accelerated growth of quantum industry and research in Australia, which, according to a recently published report by CSIRO, quantum technology will become a multi-billion-dollar business by 2040, with thousands of new jobs created. And these are not just new jobs, right? But new types of jobs, which do not exist today. Think about, for example, I don't know, like a quantum software engineer, right? Or things like that. And we're also looking to accelerate computation with quantum computers, handling otherwise intractable problems, not dissimilar to what has been happening with accelerators like GPUs or reconfigurable hardware like FPGAs, which are probably even more similar to quantum computers, given the way you implement an algorithm by designing a circuit. If, for example, your algorithm or workflow requires, say, selecting an optimal configuration out of many suitable configurations, you might decide to offload such tasks to a quantum accelerator. Now let's go to the next slide. So Pawsey quantum brilliance. As you know, we have recently started a collaboration with Quantum Brilliance, a quantum hardware startup company based in Canberra, with the goal of hosting a small room temperature quantum computer at the center and integrating quantum hardware and software with pre-existing computing, storage, and networking infrastructure. The collaboration would also include a natural field trial, running applications developed by a select group of researchers, which you're going to hear from today, coming from both industry and academia, on an actual quantum computer, of course, which is the scope of the Quantum Pioneers program. And this effort is part of implementing the recommendations coming from the growing Australia's quantum technology industry roadmap developed by CSIRO. So the last thing here is that I'm not going to discuss in detail the challenges of hosting and integrating quantum computer with pre-existing IT infrastructure, because I think Marcus is going to talk about that later. But it's important to understand that there are additional requirements coming from hosting a device which is today more sensitive to environmental conditions than standard IT equipment. Think about electromagnetic interference coming from radiations, vibration, magnetic fields, and variations in temperature, for example. And not to mention to validate, challenges around validating the actual deployment of the system, right? So now a little bit about what we've been doing until now related to quantum computing. In addition to starting a collaboration with a quantum hardware startup company, we have organized 2 seminars. One to explain to researchers not familiar with quantum computing what it is and what we believe can do. And the second one focused on quantum computing opportunities for commercial companies. And of course, we have also started the Quantum Pioneers program. Now, the Quantum Pioneers program was launched February this year. And through this program, the research groups participating will have an opportunity to get access to Quantum Brilliance quantum emulator, already available on our Nimbus cloud, get access to an actual room temperature diamond quantum computer later on, and be positioned as an early innovator to integrate quantum computing technology with classical HPC infrastructure, while solving at the same time global challenges. And then, of course, also participate in dedicated workshops and training related to the use of the quantum emulator and the actual quantum development kit. And this is just a list of the projects. I'm not going to go through them right now because we're gonna hear from most of the research groups later. And just gonna talk briefly about the next steps, which are, for the groups involved, access to the Nimbus Research Cloud and the emulating environment, onboard training with separate sessions for each project, meeting the Quantum Pioneers, that's this seminar we're in today. And then we're going to have monthly open discussion sessions. And last but not least, we're going to organize a number of workshop and training events related to learning how to run on the quantum development kit and also sharing experiences related to that. Thanks a lot for your attention. I'm gonna now just have Maciej continue the event.
Thank you, Ugo. Thank you, Ugo, for this great introduction to Quantum at Pawsey. At that point, I would like to remind everyone, because we've seen people arriving to the events during your presentation, that you are all welcome to ask questions by posting them in the chat. We have Pawsey staff looking at the chat and collecting the questions, and we will try to address them in the final part of today's seminar. Our next speaker is Dr. Marcus Doherty, from a co-founder and chief scientific officer at Quantum Brilliance. Marcus is a scientist, educator, entrepreneur, and Army Reserve officer. He is a senior research fellow and lecturer at the Australian National University. Marcus is internationally recognized as a principal contributor to the emergence of diamond-based quantum technologies, including quantum microscopy, quantum computing, and quantum communications. These technologies represent new paradigms of microscopy, computing, and communication that have the potential to revolutionize many disciplines of science and technology. Marcus' research is characterized by the application of first principles understanding of optical defects in diamonds to the innovation of quantum technologies. Marcus will discuss the technology behind the world's first market-ready quantum accelerator recently announced. Over to you, Marcus.
Thanks, Marco. That's a very glowing introduction, and I appreciate it sincerely. And Ugo, thank you very much for doing such a thorough introduction to the program and what we are trying to achieve together. I will keep this relatively short in order to place the focus on our pioneers and the projects, the remarkable projects that they're going to be completing over the next couple of months. I'll begin by just expanding upon what Ugo talked about in terms of the motivation of the Quantum Supercomputing Innovation Hub that has been created at Pawsey in partnership with Quantum Brilliance. So our big picture motivation here is to stimulate a vibrant quantum computing ecosystem, which really kickstarts the generation of a sovereign quantum computing industry and development of sovereign capability in this field. And our concept of how we see this working is that we have hardware vendor like ourselves, Quantum Brilliance, which is providing hardware, but also key software tools to a tier 1 supercomputing center being Pawsey, who can then incorporate and integrate those tools and those hardware and also supplement them with the power of their computing systems for the purposes of prototyping and simulations. And then together supporting these pioneers of industry and research. These people who are seeking to develop applications and develop solutions for science problems and industry problems. And we'll see 4 today from the Western Australia, University of Western Australia, University of Melbourne, Quantum South, and Trellis Data. And then as a result of having this critical infrastructure of a supercomputer, of hardware and software tools, and supporting these application developers, attract people from industry, people from defense and government, and people from science to see, well, what are these solutions and how can they use them? And maybe I'm going to ask these pioneers to build solutions for me that I need for my business, or I need to solve my scientific problems. Or maybe I might just start my own application development efforts using this infrastructure provided by Quantum Brilliance and Pawsey. And so this is the big picture purpose that we're trying to achieve here. And as a result, grow the Australian industry and the value that the Australian quantum computing industry can do for the nation. So who is Quantum Brilliance and what are we doing and what is our vision and aspiration? So we're a quantum computing company that develops quantum computers using diamond. And in particular, these remarkable defects called nitrogen vacancy centers in diamond. By using the very particular properties of those defects, as well as the extreme properties of diamond, our quantum computers can operate at room temperature. And they also have relatively simple control systems, which means that we can ultimately shrink our quantum computers down into something the size of a graphics accelerator card. So right now we have a simple quantum development which consists of a few qubits operating in a box, and that is immediately able to interface and integrate into computing systems. And that is what we are delivering to Pawsey later this year, is that fully functional box that can be plugged directly into computing systems to support ideas around system integration, testing how the device performs and functions in the environment of a data center or environment of a computing system, and then also providing a key proof point for the development of applications to validate those ideas against a simple qubit system. Over the next 4 years, we have a variety of technologies that we have innovated, which will be included sequentially into our technology, which allows us to shrink down the size, weight, and power, whilst also increasing the computational power of our devices until we realize this idea of a quantum accelerator in 2025. And that accelerator then clicks over. It will have 50+ qubits, and it can deliver an advantage or a benefit over a classical computer of the same size, weight, and power, which is really the key point for making a quantum computer useful to people in industry and more broadly. And it supports this very different take on what a quantum computer is, supports different applications, in particularly edge computing applications and massively parallel applications in supercomputing. So what we have at Pawsey is the following. On one side, we have a quantum emulator, and on the other side, we have the quantum development kit. And on top of these two tools, we have a full software stack, which starts at hybrid code. So someone can program in classical and quantum languages in order to perform and execute programs which contain both classical and quantum computing. This is through our use of the framework we are co-developing with the Oak Ridge National Laboratory called XACC. That framework also includes a variety of plugins, which then enables integration into those hybrid computing systems, as well as compilers that can manage those systems and compile efficiently for quantum computing devices. It also supports a variety of languages, so we're not limited to one particular quantum programming language or classical programming language. Then underneath that software stack, we have an emulator, which is an accurate representation of the performance of our current and future diamond quantum computing devices. And this encodes all those things like qubit topology, errors, as well as processing time, so that you can get a genuine representation of how long would this take on the device and how does that compare to a classical computer. The emulator also has scalable simulators, which can scale efficiently on high performance computing. And so it really enables you to execute and simulate quantum circuits at scale. So at the scale of the future devices of 50+ qubits. The hardware system, as I mentioned before, is a few qubit system, which has been designed to be integratable ready. So we can plug it into the supercomputer, understand how to optimize that interface of a computing system, and understand the effect of the environment of the computing system on that device. And then also it provides a key proof point that our emulator is actually doing what it says, and that is being an accurate representation. And with that, I will close and hand back to you, Marcha. Thank you.
Thank you very much, Marcus, for introducing us to Quantum Brilliance and your technology. Quantum Brilliance technology is extremely important for us also in the context of HPC quantum integration, and we are looking forward to working with you in the future. It is a great journey. Thank you again. We will now hear on how this technology will be utilized by researchers and industry partners from Quantum Pioneers program. Let me start by introducing Professor Casey Myers from the University of Melbourne. Casey is a senior research fellow in the School of Computing and Information Systems. He worked in the private sector for a number of years, most recently working with the quantum computing startup company Xanadu. Before moving into industry, Casey worked in both the ARC Center for Quantum Computation and Communication Technology and Center for Engineering Quantum Systems. At the University of Melbourne, he is playing a leading role in establishing technology. Over to you, Professor Myers.
Thank you for that. Let me just share my screen and okay, so display mode. Thank you very much for that introduction, and thank you for inviting me to be part of this. It's going to be quite a lot of fun, I think. So let me just start my stopwatch so that I know that I'm not going too far over time. So today I'm going to talk about some finance applications on integrated quantum computing systems. So I'm going to go through a specific problem that I think is interesting and worth pursuing on near-term quantum devices, and see whether such a problem is feasible. And that's the ultimate aim of this project, is to determine the feasibility of some of these finance applications. So I'm going to start with some motivation. Something that motivates me is some recent results that have come out of Google and the FA National Laboratory in China, showing certain types of quantum supremacy. So not just in principle, like in theory, but actually showing experimental results for quantum supremacy, where I use the term quantum supremacy, which I did not come up with, and I don't think is the best term, but unfortunately it's embedded in the literature now. This term refers to when a quantum computing system, some quantum information processor can outperform a classical supercomputer for some non-trivial mathematical task. So that mathematical task may or may not be interesting to solve some real world problem, but just the same, it is something that the quantum computer can outperform a classical computer with. And so I think we're in 2021. So in 2019, Google released these results showing that they could outperform a classical supercomputer with an improvement of approximately a factor of 10 to the 9, which is what they had in their paper. And of course, that was contested in literature a little bit. But even if you listen to some of the debate about that claim, it was still many orders of magnitude above what a classical computer could do. And then more recently, late last year, there were some results, some experimental results coming out of China showing that you could get an even larger improvement on what a classical supercomputer can do for something called boson sampling, specifically Gaussian boson sampling in this case. And so this was, I would say, even further removed from what we might consider is useful for solving useful problems. But just the same, they were able to show some remarkable results for this so-called quantum supremacy. But the race is still on to show something called quantum advantage. So I refer to these two terms as fundamentally different scenarios, but some people use them interchangeably in the literature, so we have to be a little bit careful. But I think that the race is still on for someone, for a group to show a quantum advantage that solves, by that I mean it solves a practical problem, a real world problem with a speed, efficiency, or accuracy that would beat the best supercomputers. And this figure that I've got here is a very recent figure of some of the main players in the world trying to develop quantum information processors. And I think up here in the NV Diamond part of this figure, you can see quantum brilliance for NV Diamond centers. And so you can see that there's quite a lot of competition in this area. And I guess everyone's heard of IBM and Google doing the superconducting type of things, but there's also different physical architectures out there that I would say are certainly just as competitive. It all comes down to the details, I suppose. Every scheme has their pros and cons, but I think the race is certainly on to try to demonstrate a quantum advantage. But of course, the reason that we haven't found that yet is because all of these physical systems, they all suffer from decoherence, finite qubit life times, gate fidelities which aren't exactly one. And this is a pretty outdated table from BCG, the Boston Consulting Group, from showing that just some examples of qubit lifetimes and gate fidelities. And so these two facts, the fact that the qubit lifetime isn't, as long as would be required to solve certain problems, and the gate fidelities aren't 99.9999 or something like that, mean that we have a long way to go to show a quantum advantage. And so my motivation for this particular project is to try to figure out a way to obtain a quantum advantage given these realistic devices. Okay, so yeah, I'll go into some more detail about that a little bit later. Yeah, so I guess there's two ways that you can really think about improving, showing a quantum advantage for a particular circuit. You could either make this circuit small enough such that it can run on whichever physical architecture before the decoherence kills things, or you can try to recover from those errors somehow. And so both of those topics will be examined for this particular project. So specifically what we're going to look at is a model to price options using a particular quantum circuit. So in this case, it's the quantum phase estimation circuit. So these are some details on the right, which we'll go through a little bit in the next couple of slides. Yeah, okay, great. So okay, yeah, good. So finance on a quantum computer. So I'll just talk about this really quickly because I don't want to go over time. So I guess from what I can tell, the first real results for thinking about finance problems on a quantum machine came out in 2016 using adiabatic quantum computing to look at certain things, portfolio optimization or optimal trading problems. And then a few years later, people started thinking, maybe we can try to use the circuit model to solve certain tasks. So in 2018, some results came out from the company that I once worked for, showing that you could potentially price financial derivatives with a quantum circuit. And then there's been a few more results coming out in the meantime. And so this timeline is actually a little bit outdated. I wrote this up last year. I haven't put the 2020 results in yet, but I barely have time to sort of fit those in there. So like I said, we're going to consider looking at option pricing. These are some details about options. If people know how to price these, this is you. If you don't know how to do that, that's fine. You can largely ignore this. But what I want to say is that classically, the way you normally do this is you run a Monte Carlo simulation. And so if you're given a specific accuracy that you're after for these Monte Carlo simulations, you know how these simulations will scale depending on that accuracy. When you consider this from a quantum computing perspective, you get a quadratic improvement rather. And that's the sort of thing that we'd like to be able to identify on a realistic device. So this is all based on something called the quantum phase estimation algorithm. So there's some details here about that, but suffice it to say is we have some unitary, okay, U here, okay, which has some eigenvalue theta. And the whole point of this circuit, which I have here, this schematic circuit, is we would like to find a way to back out that eigenvalue theta somehow from that circuit. And so the beauty of the algorithms for trying to price options in this way is finding a way to encode the information that we want into this eigenvalue. And that's I'm not going to go through many details of that. This is as much detail as I'm going to put. So this is what an actual circuit looks like. But suffice it to say is this circuit all it's trying to do is back out the eigenvalue from a particular unitary. And that eigenvalue has the information about the price of the option. Just a couple of things that I'll say about that before I finish up. So what we need to do in order to do this is we need to encode the probability distribution that we want to run the Monte Carlo simulation over into this circuit somehow. And we need to encode the payoff function. So for those that know something about this sort of finance, you'll know what this means. If you don't, suffice it to say that these two pieces of information need to be encoded in this quantum circuit somehow. That's all encoded in these unitaries U down the bottom. And that's as much detail as I'll put in there. But now what we want to ask is, once you do that, how can we simplify this so that it'll be feasible on a machine, a near-term noisy machine? Like I said at the start, you could start thinking about the circuit elements, okay? Trying to simplify the way that you encode the probability distribution, simplify the way that you encode the payoff function in this circuit, okay? Which would mean playing with the form of these unitaries down here, or you could do even more drastic things by chopping out large chunks of the circuit and seeing whether it works. And some proposals in literature have been put forward for chopping up parts of the circuit in this way. And by doing this, you can try to minimize the depth of the circuit. So you can minimize the number of layers of gates that you require before decoherence takes over. Okay, and you could even consider trying to eliminate the entire circuit and try something completely different. For example, using some variational techniques using parameterized circuits. So beyond that, if you can't just simplify the circuit to make it smaller to fit within a realistic system's decoherence times, you could try to incorporate some error mitigation schemes. And so this is my last slide. So in these error mitigation schemes, what we really care about is finding the correct measurement statistics for the output, as opposed to the absolute correct state that the circuit should be producing. And there are various techniques that we could do. For example, if we could tune the noise, we can make the noise larger than what it naturally is. For example, we could use some sort of extrapolation, which I have on the plot here, to extrapolate back from when the noise is at zero. So they're the two areas that we want to consider for this particular project, to see whether this sort of finance application is feasible on realistic machines. So I think I'll stop there because I'm pretty much over time. Thank you. And I think we're going to try to answer questions after all the pioneers have spoken. So I'll be happy to try to answer questions.
Thank you for that interesting introduction to quantum computing design and quantum in finance project. And also for introducing us to the problem of minimization of circuit depths and quantum error. This gives us a nice perspective on parameters that need to be considered when designing quantum algorithms and circuits in a general approach. Thank you for that again.
Okay, I'll stop sharing.
Yep. Now let me introduce our next speaker, Professor Rafael Sotelo, co-founder of Quantum South. Rafael is a researcher, consultant, and educator with a PhD in telematics engineering. Rafael was the director of the ICT department at the University of Montevideo for the last 2 decades and recently became the director of research at the School of Engineering. Quantum South works with complex optimization problems for cargo in airlines and ships, leveraging quantum computing software. Over to you, Professor Sotelo.
Thank you, Maciej. Thank you for your kind introduction. Let me share my screen. I hope you are seeing it, okay? Thank you very much. So, hello, we are Quantum South. We develop solutions in the quantum computing area. We work on optimization, applying quantum computing. We were born at Universidad de Montevideo in Uruguay, Latin America, in the south cone of Latin America. And we have been accelerated at IOT Tribe, which is an UK-based accelerator. We are honored and excited for being part of the Pawsey Quantum Pioneers program together with Quantum Brilliance. So let me tell you about our journey. We start in 2019 at CES 2019 in Las Vegas. We invited Robert Doredo, an IBM Quantum Ambassador, to visit Universidad de Montevideo. In March, he offered a 3-day workshop for students, faculty, and professionals from the industry. And we were exposed to IBM Qiskit platform. And once finished this workshop, we considered participated at the Airbus Quantum Computing Challenge. So we studied the basis. Airbus wanted to explore the use of quantum computing in 5 complex aviation problems. They were between the hardest faced by the industry. We addressed problem number 5, which was aircraft loading optimization. The challenge lasted almost all 2019 and ended by the end of October. So the problem we faced that I said was number 5, asked the best way to select and arrange a number of packages, each one with a given weight and volume in an aircraft. So the vehicle has a maximum load capacity and a maximum volume, and the objective was to identify the optimal selection of the individual package to be transported that maximize the weight transported in each trip, subject to the load and volume constraints of the given vehicle. So this is an exponential, also, I mean, there is a given exponential increase in the number of possible combinations as the number of packages increase. So the problem poses a serious challenge to be solved by classical means. Our solution was inspiring the well-known NAPSA problem, which is NP-complete. We conceived the creation of a Hamiltonian representing the problem, and we used the variational quantum eigensolver, the VQE, which is an algorithm present in some quantum computers. We use IBM's Qiskit platform and libraries and testing environments for the submission. So the challenge was a success. There were more than 1,000 inscriptions from more than 70 countries. 160 teams were actively involved during the challenge as declared by Airbus. And finally, there were 36 submissions. You can see a close-up of the diversity of regions and organizations that enrolled in the challenge. Finally, we were one of the 5 finalists, together with teams from the Netherlands and France, Italy, Germany, and China. In fact, we were the only finalists from all the Americas. Well, this is our team. We are the co-founders of Quantum South. We are professors of IT from mathematics and of physics. There are students and professionals from the industry. So since then, we have participated in many international and regional conferences. This is one, for example, in Portugal at the International Iberian Nanotechnology Laboratory, and some other in Latin America, which we have a great activity. This one is in Chile, for example, also from 2019. And in 2020, we participated at IOT Tribe, as said, an UK-based startup accelerator that gave us access to people, to funding, to events, either to attend or to present, to mentors, technical and commercial mentors, to pitch training, and to development of a business plan. So what is Quantum South? Quantum South works with complex optimization problems for cargo in airlines and ships, leveraging quantum computing software. The goal is to achieve better results than conventional solutions available today and help companies to improve revenues and reduce costs. These are our lines of commercial lines, that is for airline cargo, maritime cargo, which is much larger problems, for financial services that, given the combinatorial optimization problem, it has the roots are very similar. The roots of the program are very similar to the ones we already addressed. So how is it done today? There are a lot of restrictions, there are limited time, and the software optimization is done through best practices and limited space linear programming. Our solution is a software product integrated to legacy systems that, based on cargo to be dispatched in an aircraft or ship with limited capacity, will provide the best allocation based on cost and revenue restrictions. The core optimization algorithms are based on quantum computing technologies. So this is the architecture of our product. We need to integrate with legacy systems, then prepare the data of each specific run of the algorithm, apply it to a particular instance of the problem, and finally send it to the quantum computer to run the algorithm based on BQE to obtain the best solution. This is our timeline for the next year. We are developing the products and offering consultancy. We plan to make proof of concepts and pilots with specific clients. Sorry, I am here now.
Yes.
Okay.
Continue. Yeah.
Sorry about that. Well, we feel integrated in a global ecosystem. We participate in many events. For example, in IEEE Quantum Week, we organize a workshop on quantum computing entrepreneurship. We share stage there with Quantum Brilliance, and we participate in Slingshot startup competition last year. We made the top 500 startups. We made contacts with DHL, Lufthansa Cargo. We also participate in Singapore's Airlines Challenge. We are organizing a Quantum Latino, that is in Latin America, an event, a quantum event in Latin America. And so far we have worked with platforms from the following vendors: IBM, Amazon Web Services, D-Wave, Cambridge Quantum Computing, Microsoft, and of course, Quantum Brilliance. We are working in collaboration with them at Pawsey Supercomputing Center. And we are in contact with other major vendors like IonQ, Honeywell, Fujitsu, Google, and Atos. So a special chapter for Microsoft. Our mother university is part of Microsoft Quantum Network, one of 20 universities in the world, and the only one in Latin America. That paved the way for us to make a course on quantum computing. We have had more than 30 people training in developing software for quantum computers. And finally, well, I want to highlight that Quantum South and Quantum Brilliance are working closely together in demonstrating quantum advances can be achieved with fewer qubits in logistic optimization applications when combined with Quantum South software. So our technical team is working close with Quantum Brilliance technical team. Our team is currently accessing Pawsey Supercomputing Center and working with Quantum Brilliance Quantum Emulator, that is QBQE software. And we also have commercial cooperation exploring applications in logistics and other fields which require combinatorial optimization. So that's the end of my presentation. Thank you very much. Back to you, Asik. Thank you.
Thank you for sharing this interesting presentation. It's really great to see that multi-continental collaboration that we were able to build within Quantum Pioneers program. And we also see that solving complex optimization problems is an extremely important and promising application of quantum computing. And it finds a direct use in various branches of industry. Thank you so much for introducing us to that class of problems. With that, let me welcome our next speaker, Professor Jingbo Wang from the University of Western Australia. Professor Wang is the head of the physics department at UWA and a pioneer of cutting-edge research in the development of quantum walk-based algorithms, aiming at solving complex problems of practical importance, otherwise intractable. Her research team was among the first to show the power of quantum walks in extracting local and global structural information of complex networks, in distinguishing large sets of non-isomorphic graph classes, and finding optimal, high-quality solutions to a wide range of combinatorial optimization problems, in speeding up machine learning and information processing, as well as in exploring fundamental structures and symmetries in nature. Professor Wang is also the chair of the QUISA research cluster of the topical group for quantum science and technology under the Australian Institute of Physics, and a member of the World Economic Forum Global Future Council on Quantum Applications. Professor Wang, the virtual floor is yours.
Thanks, Maciej, and thanks for the invitation. I'll start to share my screen. Yeah, as Maciej mentioned, we are currently forming a research group on quantum information simulation and algorithms. So we have been working in this field for the last 20 years, but we are also very surprised to really see this current very rapid development in the area, which is great. So today I'll pick a particular topic to talk about, which also touches the same kind of area as the previous two speakers. Thanks, Casey and Rafu, for your really nice description of the problem and your work. Actually, Rafu, you mentioned about this Airbus quantum challenge, and I was on the jury. So I did read your proposal, and which was yeah, highly regarded, so which was nice. Thanks for that report of the continued effort. Okay, so combinatorial optimization, as many of you know, it's really important in all areas of science and engineering, practical applications. It's a process of identify optimum or high quality solutions. But hopefully, ultimately, you need to evaluate all possibilities from a finite side, but which can be exponentially large. It's known to be NP hard. It's more than beyond the NP complete. So it's notoriously difficult in general to solve. Just the number of possibilities is just too large to search exhaustively and accurately. I'll just give a few examples, and actually Casey and Rafu has mentioned a couple. For example, if we want to find out the optimum solution of placing a bag with 40, let's say, valuable items out of 100 items, we are dealing with more than 10 to the power of 28 possibilities, which is large, yeah. So if we, I think Casey actually put a number there, the current capacity for the most powerful supercomputer is around 10 to the power of 16. So this is much bigger than we can actually encode it into the hardware, even into the memory, not let alone to process it and try to pick out the most optimal one. The other area of research is the drug discovery. So if you want to compare some molecules with 50 atoms, just to say whether they have some kind of similar topology even, it requires a search space of 10 to the power of 48. Another typical practical problem is, let's say, traffic control. So if we, let's say, if we consider some kind of starting and ending points in some kind of network, let's just try to find 5 pairs of starting and ending, and through a network of reasonable size. We are talking about 10 to the power of 100 possibilities. Casey in particular mentioned about finance problems. If we want to optimize some kind of financial portfolio, let's say we have 500 stocks to select, even just a handful quickly goes beyond 10 to the power of 150. So all these kind of problems cannot be solved really with even the most powerful supercomputers combined together. And as you can imagine, if we are able to provide a quantum solution, it will be a game-changing strategy, and it will help enormously in all fronts. I'll just use a very simple example to illustrate what we need to do in order to code the problems into a quantum computer and trying to find high-quality solutions. So here is a very typical graph partition problem. Here, what you want to do is to partition the graph into two groups, and you want to make sure the interconnection, the edges, is the minimum. So here I gave some examples that would have a quality of 7. So the interconnection edges are 7 and 5 and so on. So if you go through all possibilities, and then you encode your problem as a set of quality values, and really the aim is to find the minimum of all. So what do we do? What do we have? If we have a graph of 100 nodes, which is a very small network actually, quickly exhaustive search space will be 2 to the power of 100. And just to remind you, the most powerful supercomputer we have is in the order of 10 to the power of 16 bit of memory. So this far surpass what you could possibly do. But if you take the log, and which is the power of a quantum computer in terms of qubits, and 70 qubits will be able to encode information of 2 to the power of 70, which is 2 to the, which is around what we will need. So I just found this paper actually yesterday, published in Nature Physics, in March. That provides, I'm just trying to remove some things out of the screen so I can see a perspective of what we are. So as I mentioned, this Summit supercomputer, which was the most powerful supercomputer until possibly a year ago. And it has a very large memory space, 10 to the power of 16. So that's the state of the art of what we have in the classical domain. And that has been developed all the way since, if we consider the first electronic computer, and now it's almost 80 years. So this is what happened in the quantum domain. The whole idea started around 1980, and the first idea possibly was from Richard Feynman. He was asking, let's be crazy, let's start to think about a quantum bit or the memory or the gates, not based on millions of electrons or based on some kind of current or voltage. Rather, let's encode things into single particles and what would happen. So that triggered a flurry of theoretical research, mainly in the domain of what we call quantum foundations. Try to figure out really whether that can actually help us to understand nature in a much deeper level. So the real development happens around 1995 when Peter Shaw proposed a magic and exponentially efficient quantum algorithm, which actually demonstrates it's going to have a very significant practical use. That has driven the field from 1995, which is barely 20 some years. And for many, many years, even just like 5 years ago, all the labs around the world are talking about single qubit. And if you can achieve a 2-qubit logical manipulation, which was considered a very big advance. And merely, you can see, merely 5 or so years, we have moved from a couple of qubits to 54. And that was demonstrated last year by Google. I have something, yeah, okay, hopefully this is better. And why 54 qubits? 2 to the power of 54 is about twice of what we have for this most powerful supercomputer. And if you try to think about how can we increase our capacity in the classical domain, you basically have to build another Pawsey to have another equivalent Pawsey computer. While here, if you add 1 more qubit, 55, and immediately you double the capacity. So the promise is there, but it also has daunting challenges along the way. So we don't really know how fast and how quickly the technology is really going to be taking off in the practical, commercial, everyday life. But the promise is so attractive. And that's why this field has been taking off just exponentially. The number of papers, the number of people working in the field is just, phenomenal. Okay, so that's the background. And I'll talk about a particular approach we have been developing, and we believe it has a very significant advantage over many other methods. It started with this idea that's not new, and this is really behind the earliest commercial companies, which is called D-Wave. So I'll quickly describe what it is, and then I'll move on to what kind of improvement we need to take in order to make this a useful and a practically useful algorithm to be implemented, hopefully in the near future or current quantum processors or quantum accelerators. So this is the Schrödinger's equation, and which describes the dynamics of all quantum systems. So this algorithm is based on the quantum adiabatic theorem, which says as the following. So the quantum system is governed by this Schrödinger's equation through its Hamiltonian. So the Hamiltonian here, as you can see, that's the change of your system. That's how you are going to change. And this Hamiltonian includes all the interactions within the system and with the environmental control. So if you have a Hamiltonian, which is very simple, and you can solve it analytically, and you can prepare its ground state easily. The challenge is we encode our solution of a combinatorial optimization problem as an example, in such a way which is very difficult to solve. So if you can solve it, and then the problem is solved. But we are trying to drive the quantum system through this adiabatic process where it says, okay, so you gradually change your Hamiltonian with time from a very simple, very easy to prepare ground state to your solution. As you can see, t equals 0 is completely B. When t is t, the final time, it will be completely Q. At that time, the ground state of this Hamiltonian will be your solution. So this theorem says if you drive the system very, very slow, and the system will follow every step, every tiny increment in time is basically a very small perturbation. Because it's so small, you are not going to excite it to the upper states. Okay, so that's the basic principle. The downside is, that's the reference if you want to follow, you have to go really, really slow. And the system can be quite complex, and it's becoming more and more complex if you introduce more and more qubits. And this kind of scenario where two curves approaching each other happens all the time. When those two curves approach together, this is the ground state, and this is upper states. When it comes to so close, it has very significant probability to be in another state, which is not going to be a solution. So what we did is...
I'm sorry for interrupting. Professor Wang, we have 2 minutes.
Yes, I'm going to wrap it up. Yeah, so 2 minutes is enough. So what we did is trying to improve it, and we are not going to assume this process can go too very long. And we have a fixed circuit depth. For example, we say we only allow 50 logic gate manipulation, and that step would be 50. And we are trying to find a way to achieve the highest possible quality solution. It will possibly not be going to be the optimum solution, but it's going to be the 1% or 0.0001% of the highest solution. I don't have time to get into the details. I just want to say our task is really simple here. It's trying to design a quantum circuit, and the depth is restricted to be 50, for example. And in terms of quantum work, and the topology has to, we know what needs to be. For example, it needs to be this kind of Mobius kind of connection. And if we can do that, okay, there's some books. If you want to read the details, you can. So finally, I'll just show this animation, and I'll end. Yep. So you can see this is what we do. We start the size of the circle represent the probability of finding that particular solution. So we drive the change, right? And then we change the phase. I will drive the change again. These are all coming from the solution of Schrödinger's equation. And towards the end, we are hoping the solution will be converged to the best one. And one more step, it will be. And now you can collapse your wave function by measurement, and the probability of which solution it will be collapsed into is determined by its amplitude in its wave function. And in this case, these two are equally good solutions. And you can see they have almost 90% in this case. Oh, yes, 90%. I'll stop here. Maybe finally you can say we only need 70 qubits, which hopefully is not too far away.
Thank you so much, Professor Wang. And I'm really sorry to interrupt your presentation. Okay. It was a great presentation, and I also see a very positive reactions in the chat. Thank you for introducing us to this important application of quantum computing. I would also like to mention the close collaboration Pawsey has established with Professor Wang Group over many years through supporting her allocations and projects on Pawsey supercomputers and the work of her students through the Pawsey internship program. It's always a great pleasure to listen to your inspiring talks. Thank you, Professor Wang, again.
Thanks. Yeah, that's actually the one more thing I want to say is over the last almost 20 or 30 years, started with IVIC and now Pawsey every year. And we are able to do what we are doing because of that. Thank you.
Thank you again. As we all know, nowadays, optimal scheduling of meetings and events is also a very complex task. And unfortunately, because of that, the representatives of the fourth Quantum Pioneers project couldn't join us today because of the conflicts with other meetings. However, I would like to use just a little bit of time to introduce their project. Trellis Data, an Australian-based tech company delivering sophisticated machine learning solution, is the fourth member of Quantum Pioneers program. To overcome machine learning computational bottlenecks faced by classical computation resources and reduce error risks, especially in the context of mission-critical operations, Trellis and Quantum Brilliance are proposing or working on a solution in the form of hybrid quantum machine learning decoder for natural language processing. The solution will be suited for near-term noisy quantum computers. A recurrent artificial neural network efficiently process the input signals to large size probability tables, and quantum routines accurately find the most likely solutions. We are all looking forward to work with all Quantum Pioneers projects. Pawsey will also work closely with Quantum Brilliance to provide you with all necessary tools and support to make this collaboration a success for all. And for the participants, please keep track of all quantum activities. There will be numerous opportunities to get involved. With that, we will now open the floor to questions collected through chat. So please give me a second. I will switch to my screen with questions. I saw there were a lot of questions, and some of them were already answered in the chat. Thank you, Casey, for taking some of those questions. The first one I would like to mention is a question from Sam Young. In classical computing, number of bits of a CPU refers to data bandwidth, and number of binary gates in a CPU is related to its complexity and processing power. It appears that qubit refers both to data and number of quantum gates in a CPU. What is the reason for using qubit for both data and hardware capacities? Or is it my misunderstanding?
Yeah, may I answer that? Yeah. So number of qubits is really, if you can think about them as memory, right? Then you can process the information stored in that memory. So that's very, very important. And when we talk about number of quantum gates, it's the number of quantum actions you have to apply to those qubits. And because the information can be stored in the number of qubits is 2 to the power of n, and we are restricting our quantum operation to be poly n, not poly 2 to the power of n. So that's why when people talk about number of qubits, and you are expecting the number of quantum manipulation or quantum logic manipulation would be in the polynomial of n. So that's where the people are, yeah, that's implied. So they are separate things. They are separate things. The number of logic manipulation, the number of qubits, they are related because we believe what we have to do is in the order of poly n operations. Hope that's clear. So it's really important. Yeah, if the number of operations required is in the order of 2 to the power of n, it's much better to do it in the classical world. So there is no real reason to use a quantum computer. In general. If I may add, So there, okay. So there are polynomially more efficient quantum algorithms like search, like the like the Grover's search, which is a square root, and then the number of operations will be square root of 2 to the power of n. So the saving is not going to be exponential. However, it's still a very significant saving.
Thank you so much, Professor Wang. There were a couple of other questions. I think that the second one that I would like to mention is was partially already answered by Casey in the chat, but let me read that loudly so for all of us. If an architecture manages to reach quantum advantage, does that render other architectures moot? Or could there potentially still be the promise of certain hybridized systems, two architectures paired together? So I think this is a question about classical and quantum working together in the future.
Marce, if I may, I might take this one to lead off with and then invite others to join me. I'll just quickly share a slide, which I think sort of talks to this point. So give me one moment. And so the likely future that I see is that there will be a variety of quantum computers in the world. And these quantum computers will occupy different roles. And those roles are a centralized role where you can think of a single entity being a quantum supercomputer or a quantum mainframe, or many quantum computers integrated into the racks alongside the classical CPUs and GPUs in a massive parallelization form. And then beyond that centralized computing, we can think about distributed computing, where we now have network computers occupying various places, such as in a medical imaging suite or other sorts of centers. And then we have mobile things, which are now edge computing devices. They're compact, they're rationalized in terms of weight and power, and they're doing things like operating in satellites and remote cars. And different quantum computing technologies, different hardware technologies are better suited to these different roles. So each hardware technology has a strength and weakness, and that means that they're more or less suited to these different types of role of centralized, distributed, and mobile/edge. And so I think that means the reality is a future which contains multiple different quantum computing hardwares, and also will always contain multiple different types of classical computing hardwares. And in nearly all instances, quantum and classical computers are working together. Perhaps the one exception would be this idea of the quantum mainframe, where it's only operating at arm's length with a classical computer. So that might frame some answers from my other colleagues on the panel.
Okay, are there any other comments on that particular question? If not, I will move to the next question. So
I believe Jingbo wanted to participate, Masha.
yes,
Yeah, absolutely. I agree with Marcus fully. And I think that's what we are currently doing. And we start because, as I mentioned, we are not expecting a full scale universal quantum computing anytime soon. So what we have, as I think Marcus also mentioned, it's a quantum accelerator. So what we think about is the classical world, the dimension is small. So we have a problem which has to be explored in a very, very high dimensional world. So what we are saying is that the classical computer sends the information to this huge Hilbert space to explore about its symmetry, about its structure. But towards the end of the day, it cannot be measured. Quantum computer will have all the information, knows about every solution, but we don't. So it will have to project it back to our world, and which is much lower dimension, and do the processing. So if our world is too small, that collapsing of wave function will will lose all the important information. So we need as large a space as possible in the classical world. That's why this summit or Magnus, all those classical supercomputers will be vital for us to be able to understand a much bigger world.
Thank you, Professor Wang and Marcus. I'll read the next question. So the next question is about how can aviation companies benefit from optimization solutions? So I think that's probably a question for Quantum South and the actual application of your algorithms in industry.
Yes, thank you for the question. You know, we have been, after the challenge, the Airbus quantum computing challenge, we have been thinking why they ask that. And we have been digging in figures from the market, and we found reports from Boeing and from the international, from IATA, that is the association from the International Association of Aviation. I mean, and their figures say, for example, there is a problem with the load factor. I mean, for example, in 2017, the load factor for passengers was over 80% in average in each flight during the year. On the other hand, the load factor for cargo was about 50%. So that shows that there is a great room for improving that. And the market for air cargo is higher than 100,000 million US dollars. So it's enormous. So the teeniest percentage you can improve that, it is an enormous savings, implies enormous savings. So that we think that is something that may drive the introduction of quantum optimization in the next year in this industry.
Thank you so much for that answer. I would like to mention another question, which is, I think, very relevant to the actual collaboration between Pawsey and Quantum Brilliance. So there was a question about, are there any existing quantum supercomputing hubs currently in the world?
Perhaps I'll start off, and then Ugo, if you'd like to join after me and give your perspective, that might be a good way to go. So there is a variety of national initiatives across the world, and many of these national initiatives include something that look like either a national quantum computing facility or center or a hub. And so we can look to the United Kingdom, where there is the National Quantum Computing Facility, which is alongside their national supercomputing facility and is looking to integrate and do work together and support an industry in the UK. In the European Union, we see both France and Germany creating these hubs around their supercomputers. And a classic example is the LRZ in Munich, which has created a quantum supercomputing integration center, and they're looking to study integration, very similar to what we're studying here with Pawsey. And you can see similar examples at the Jülich supercomputing facility as well in Germany. In the US, we see the very large national labs like Oak Ridge National Labs and also Argonne National Labs, who have substantial quantum computing programs as part of those national labs, and they are naturally alongside the supercomputing facilities that exist within those national laboratories. So this idea of taking quantum and supercomputing being a natural home for it is around the world. with all these nations who are really leading and driving the evolution of quantum computing. And so the Pawsey Quantum Brilliance Partnership is Australia's effort in which is similar to those other strategic national initiatives in other countries.
Marcus, since you mentioned my name, I'm going to say a few things here, but I was about to mention the same places you just mentioned yourself, right? So yeah, in particular in Germany, I think they allocated 2 billion euros for just to quantum technology just a few months ago, right? I happen to know that area of the country quite well, LRZ, Garching, and the thing there is that which is kind of unique, is that in one place, they have all the competencies needed, right? They have a supercomputing center with computer scientists, computational scientists. They also have physics labs there, all in the same place, right? So that's what you need. You need to bring in competencies from many different areas, right? And that's also similar to what they do at other places, but that area there, I think it's probably a very good example of how we should approach this challenge, right? Bringing in all the different competencies from different domains. That's it. Yeah. And of course, you mentioned Oak Ridge. Oak Ridge, we know that they got $115 million not long ago just to develop quantum expertise. But it's a little bit different there, right? Because they also do have all the competencies on site. But in Germany, they have many centers, all sitting in the same place physically, right? So it's quite unique, I would say. Yeah.
Thank you, Ugo and Marcus. I think I will also so that's the last question for today's panel. I will also mention that there was an information in chat about the New South Wales Defence Innovation Network challenges, which some of them are related to quantum computing. Thank you for all the discussions that we had in the chat and all the responses that were provided to other questions there. With that, I would also like to thank all the presenters for their inspiring talks and all our participants for your interest and time. Pawsey online seminars, which we started to run more or less a year ago, have been a great success so far. Thanks to our great speakers and participants, as well as the Pawsey team supporting the event. So huge thanks to Karina and Aditi and other people involved in that. Please remember to fill out the survey. We always value your feedback. Please contact us if you have suggestions or proposals for future events. With that, I would like to wish you all a very good weekend and thank you all.